Okay, I'd like to talk about F divergence today. It's by Ali M. Silve in '66. It's called F divergence basically because we usually generate this with a function f. That function can be either convex or concave. And since f is either convex or concave, then if I define gx as fx over the second derivative of f at 1, let's say, then it's a convex function, because if f is convex, then f double pi 1 will be equal to, it will be positive, and if it's concave, then this will be, f double pi will be negative, then a negative concave function will be convex, therefore, like in either case, gx will be convex. Then let's consider this expression here. Okay, this one, as one can think of this, is very much similar to the KL divergence, that instead of we have a log function here, we have a g function here. There's this g function is convex in this case. And if one recall the inequality in the KL divergence, that's inequality we use quite often, that basically we have a log x is bigger than equal to x minus 1. And in this case, basically it's just saying that like this function g is bigger than is always bigger than equal to a linear, the tangential linear, the line just intersect at 1 here. So, and this line is basically just expressed by g1 plus g pi 1 times a minus 1. Of course, I can also consider this is a Taylor series expansion up to the first order. And just as shown graphically here, I know that GA is always bigger than this line here. And so therefore I can substitute this into here, and I will have like this is bigger than equal to qx times g1 plus g pi 1 px over qx minus 1, take the integral, and then I can just kind of expand the term here, and I got this. Now let's define the F divergence basically as this expression minus this whole thing here. So basically it's this minus this guy here, so I just regroup the term like this, and then I substitute g by f, gx by fx over f double pi 1. So therefore I have this here, and this is our expression for the F divergence. And from our discussion here, we know that like this always bigger than this term here, so therefore I have this definition of the F divergence is always bigger than equal to 1. Bigger than equal to 0. And also when only when px and qx are the same, that basically px over qx equal to 1 for all x, or at least for all x such that qx is bigger than 0, then this integral will be equal to 0. So, or in other words, just summarize here. So I always have the F divergence is bigger than equal to 0. Moreover, I only have this is equal to 0 when I missed that. It's equal to 0 only when px is equal to qx for all x when qx is not equal to 0. And that's a very quick. Okay, I'd like to talk about next is a special case of F divergence known as the alpha divergence. So it's a special case basically just by substituting fx as alpha to the x, where alpha is any real number from negative, like you can all the way negative infinity to infinity. And Then let me just substitute f into that. Then we'll get this expression here. Let me just rewrite it like this. This is a more commonly found form in the papers. And in particular, it's interesting to see the different alpha values for different the alpha divergence for different alpha values. For example, for alpha equal to 1, of course, for alpha equal to 1, it's not exactly defined as I have a denominator here which goes to 0. But I can take the limit and basically use the L'Hospital rule. We'll take the derivative for both the denominator and the numerator. Taking the derivative for the numerator, I got 1 minus alpha. That's basically 1 minus 2 alpha. And the denominator, I got px minus qx minus qx, px over qx to the alpha and log px qx. So here we need to be careful that we're taking derivative with respect to alpha here, not with respect to p or q. So there's a tendency you want to like pull alpha down and something like that, but alpha here is this variable instead. And we substitute alpha equal to 1 now. Then we got this expression, and we just rearrange the term. What we can see here is actually this is just the KL divergence, or like the unnormalized form of the KL divergence between px and qx. Similarly, we can look at like for alpha equal to 0, and again like this is not exactly defined, so we just have to take the limit there, and we just repeat the same procedure. If we substitute that, we get basically the term here is just the again a normalized KL divergence, but this time is from qx to px.